Hi, and welcome to our talk today on Magma and scale-out networking for next-gen mobile networks. Over the last several decades, scale-out networking techniques have been used by internet applications to reach unprecedented scale. Yet these same techniques have not been widely deployed among telco applications. Joining me today is Shadi Hassan from Virginia Tech University, and I'm Phil Ritter, representing Facebook Connectivity and the Magma Core Foundation, to talk to you about scale-out networking for next-gen mobile networks. Shadi?
Thanks, Phil. To start out, I want to provide some quick acknowledgments to the folks who helped make this talk a reality. So first, of course, the whole Magma community. And in particular, I want to thank Amar Padmanabhan, Ulash Kuzat, Shahraman, and Tariq Al-Kasab for articulating some of the key ideas that we'll be talking about in this talk. But any mistakes are solely my responsibility. So I want to take us back to the early days of telephony to begin. So if you imagine that you're in the United States in the 1950s and you're picking up your phone to make a phone call. Your phone call is going to be sent to a switch that looks something like this in some building, many of which were distributed around the country. At the time, the mobile or the fixed line phone network was the most important communications network around. And if we fast forward to today, the equivalent of what a phone switch looks like in a modern mobile network looks something a bit more like this, very futuristic and modern. But at some level, it's essentially shares some similar underlying principles. There will be a data center somewhere connected with lots of networking switches and routers, and some of the core services necessary for running the mobile network, what we refer to as a mobile core, are going to be running on servers, potentially virtualized within this data center environment. And things have changed a lot since the 1950s in the world of telephony. Mobile networks today cover more than 95% of the world's population. And there's more than 5 billion people and 20 billion devices on mobile networks regularly. According to the different sources that you can find, this is an example from Ericsson, there's an estimated 66 exabytes of traffic on mobile networks every month. And unlike the telephony network in the 1950s, mobile networks today support a wide variety of applications beyond voice. We also support video, data, Internet of Things, all running on the same underlying infrastructure. And most of this infrastructure, particularly on the client side, is probably running ARM. But at the same time, I would argue that despite these changes, a lot of things are actually pretty similar at an architectural level. So if we think about how we actually use a network today, just like in the 1950s, we pick up or turn on our phone. When we turn on our phone, it's going to connect to a giant mobile core that's run by our mobile network operator, just like the phones of the 1950s connected to a telco's giant switch. All of our traffic is then going to go to that mobile core, and the mobile core is solely responsible for deciding what to do with it before our traffic is allowed to reach the internet. Any network policy, charging, and so forth is going to be implemented on path by that core switch, just like done in the 1950s. And if your telco wants to support more traffic because it's growing and successful, it needs to buy a bigger mobile core, just like AT&T would have had to physically upgrade their switch to a larger one back in the 1950s. And similarly, if that mobile core breaks, there's a potential for the entire network to stop working, or at least a significant chunk of that network. And this is something that still happens today. Those of you in the United Kingdom may remember a few years ago when O2 had a day-long network outage after a certificate expired on part of their mobile core. In the US, some of you may remember last year when the T-Mobile voice over LTE network failed and disrupted calls for a number of hours. And just a few months ago in Australia, Vodafone suffered a nationwide outage for similar reasons. So what I would contend is that there's no easy fix for some of these underlying architectural shortcomings of the way we build mobile networks today. 5G introduces a service-oriented core, but it still relies on centralized enforcement of network policy. At the end of the day, there's some centralized on-path device that's making authentication decisions for a wide portion of your network. And while network function virtualization can make it easier to scale and replicate individual elements of the mobile network core, it doesn't address the root problem. Fundamentally, in mobile networks today, correct operation of the network relies on network state that's replicated across multiple mobile core elements, each of which is operating independently. If we want to make some policy happen in our network, we have to synchronize that state across many different parts of the mobile network, reaching all the way out to the radio and in some cases even to the user's handset. For any of you who have worked in modern large-scale distributed systems, you know that scaling this out gets really tricky really fast. And debugging failures in such a system also become very difficult. And so in practice, even if we can scale our network functions virtually, we still have to keep them centralized. For a mobile operator, what this means is that when things break or when you want to innovate and try something new, you are constrained by these fundamental limitations of the cellular architecture today. And other networks have looked like this in the past. If we think about the way hyperscale data centers used to look, they suffered similar shortcomings. Network policy in the data center was implemented in on-path choke point devices, like firewalls, for example. And if you wanted to scale your data center, you had to invest in special purpose dedicated switching and routing hardware. If you needed some new functionality from your network, your only option was to buy some new hardware and hope that it's sufficiently reliable and can integrate easily with your existing system. But modern data centers don't have these problems. We've solved some of these issues, even as the workloads that those data centers have to run have become more complex. Today, a modern data center will be running workloads in virtual machines or containers, potentially containers that might have to move around between different hosts within the data center. And this leads to highly complex and dynamic policies that the network has to be able to support. And of course, these data centers have massive traffic volumes. The way that data center operators were able to scale was changing the way they thought about architecting their network. Rather than relying on dedicated hardware devices, we moved to software packet processing on commodity hardware, taking advantage of the capabilities of modern CPUs running at the edge of our network. We recognize that the edge and the fabric, that is, the portion of the network responsible for actually connecting hosts to each other, play very different roles. The edge can be policy rich. The edge knows what applications are running on it. The edge has a highly capable CPU. And so we can move a lot of the complex decision making out of dedicated devices and into our edge. And at the same time, the fabric has just one job: to move packets as fast as possible between hosts. And this realization lets us think about new ways of modularizing state management. And once we change the way we think about managing state within our network, we get to a network architecture that has very different scaling and resiliency properties. In fact, we can start thinking about building our network like a modern distributed system rather than like a telephone network in the 1950s. And so Magma is our approach to think about how we bring these modern networking principles to the mobile core. So imagine that you want to build a mobile network today. You have some radio infrastructure that you've distributed, set up all across your area that you'd like to provide service. In Magma, rather than deploying a single centralized core network, we introduce an element which we refer to as an access gateway. And the access gateway is co-located with all of your radio elements at a conceptual level, and it provides the runtime abstraction for our system. 3GPP, or mobile signaling traffic, is going to enter the access gateway, and what's going to come out the other side is user-level IP traffic. And the access gateway is able to do this with full policy support. From a state perspective, the access gateway is responsible for operational state within the network on the data path. These are things like the UE status, potentially metrics that are being generated. But at the same time, the configuration state for that access gateway, that is both how the device itself is configured, as well as more importantly, how the network policy is configured, is authoritatively owned at a network level. And it's derived and rather compiled as a function of that network-wide configuration for a particular access gateway. And these access gateways are simple devices running a general purpose CPU, such as an ARM chip. The other key architectural component for Magma is the orchestrator, and this provides our configuration abstraction for the network. The orchestrator is logically centralized and allows network operators to express their network configuration and policy via a rich set of REST APIs. The orchestrator provides the authoritative, durable configuration state for the entire network. It's essentially a big graph representation of your network with entities and edges and policy defined for each element. Critically, the orchestrator is not on the data path. It's only used to configure access gateways and other Magma elements. And you can deploy the orchestrator either on a public cloud or a private cloud environment or on an on-prem installation. It's a microservice cluster. And so let's think about some of the principles that we used for developing Magma. Once we have all of this together, we can simply connect all of our access gateways over the public internet and provide service to our users. So the first key principle behind Magma is modularization. Any traffic on the internet that matters today is IP. We don't need to rely on specialized services for the vast majority of user traffic that are going through operators' networks. In Magma, we decided to move policy enforcement to the edge as close to the radio access network or RAN as possible and into software. And in doing so, just like in the data center, we can let the IP network stay really simple. It becomes cheaper, it's faster, and more flexible. Once we do this, scale up becomes really easy because we no longer have any centralized on-path components. We're simply reusing the existing routing and switching infrastructure for our networks. And the picture on this slide is actually a great example of some of the benefits that you reap through this modularization principle. This is a photo of the deployment of one of the first Magma sites in existence that a ISP in Peru deployed. And within the span of a day, they were able to take their existing IP network, their Wi-Fi-based IP network, add a single access gateway and LTE radio, and begin providing LTE service to their clients. The second principle behind Magma is its use of declarative encapsulated state. Like I mentioned earlier, today's mobile cores synchronize state across the entire network for every device. And it becomes really difficult to reason about this state because everything is event-driven. The image on the right is the signaling flow for a handover in a mobile network. And as you can see, for a single user moving between two different radio elements, there's 5 different network elements that have to be involved in that procedure, each of which are storing replicas of key variables that have to stay in synchronization. If there's a bug in any of these elements, or if one element has a failure, or if a message is lost, it becomes difficult to reason about how to recover from that failure gracefully, or even to think about how to implement such a thing from scratch. Magma takes a very different approach. We aim for eventually consistent declarative state. We manage our network based on levels rather than edges. The idea here is that we'll define the state that we want a given network element to eventually converge to, and we'll let that element figure out how to do that on its own, rather than simply responding to messages as they come in. This gives us a principled way to think about state management in the network, and it helps us encapsulate our operational state at the edge and remove some of the leaky abstractions that exist within today's cellular networking protocols. Our third principle when we think about how we build Magma is to try to limit our failure domains. A failure domain, it helps us think about the question of when, not if, something fails, what is the blast radius that it damages. This is a critical question if you're a network operator when you're reasoning about the resiliency and fault tolerance of your network. Like we've discussed, in today's network, a single element can take down entire nation-scale networks. For Magma, we tried to limit the fault domains to the smallest components possible, and we assume that individual components will fail on a regular basis, and instead design our system to be resilient to failure. This is the way we build modern data centers and modern cloud applications too. It lets us move fast in spite of things breaking and deliver upgrades at the speed of software rather than at the speed of hardware, without necessarily having to resort to once per quarter maintenance and upgrade windows. Critically, the most important source of network failures, intentional configuration updates, we're able to limit the scope of what happens when those go poorly. And to give you an example of what limiting failure domains allows us to do, at the start of 2021, Magma as a project actually had no 5G core support in its release. But with our quarterly release process, 5G core support will be able to be added into production networks by the end of the year. So with these principles and the architectural components that I laid out, we've solved our scaling problem at its root. We still have a centralized orchestrator, which helps us do management easily, but it's no longer on the critical path. It's just storing a graph with configuration state. All of the runtime state necessary to serve a user is generated from configuration by every access gateway. This obviously enables some great scale out and resiliency properties, but it also lets us do some pretty cool tricks. Let me show you a couple of those. So if we remember that we have two key components in a Magma deployment, we have a collection of access gateways deployed towards the edge of our network, connected to the public internet, and managed centrally by an orchestrator. Say we want to push out a software update to our access gateways. In many cases, Magma actually allows zero downtime software upgrades for certain elements of the services running on the access gateway. But perhaps we're pushing the most disruptive update possible. Maybe we're making a really risky configuration change. Magma lets us do rolling upgrades. So in the worst case, if that upgrade goes wrong, our failure domain is going to be limited only to the access gateway that we are actively upgrading. And you can use this primitive to do things like canarying configuration changes or upgrades and trying them out on a small portion of your network first, letting them run for a while, seeing if they work, and then incrementally rolling out your upgrade to other portions of your network. And so even in the worst case, you're only losing a small portion of your network if something goes wrong during your upgrade. This is really tricky to do in a traditional mobile core. Another cool thing that we can do is implement high availability in a kind of clever way. So if you'll recall, every access gateway simply implements a function of the globally defined configuration state. And in that sense, access gateways are functionally interchangeable. So one of the ways that we can implement high availability using Magma is have a single radio node connected to multiple access gateways simultaneously, using one as a primary. And so in this example, we would typically use the access gateway that's co-located with the radio for user traffic, since it's more efficient and it helps us scale out well. But we could have a backup link to another access gateway, say even hosted in a cloud environment. If for whatever reason our connection to our local access gateway fails, that radio element could automatically reconnect to a cloud-hosted access gateway and restore service to users with just a small disruption. And if you start to think about this on a network scale, rather than having to deploy pairs of access gateways to achieve high availability or replicas of a centralized mobile core, you could have a small collection of standby access gateways hosted in a cloud environment that are only spun up when necessary to provide service to access gateways that fail in the field. So this is pretty cool, and again, very difficult to achieve in a traditional core design today. So I'll give you a quick look of what the access gateway looks like on the inside. So in a cellular network, you can essentially think of two streams of data coming off of your radio network. There's the user plane or the data plane, which is actual user traffic destined eventually for the internet, as well as a control plane that's used for signaling and kind of controlling devices as they move around the radio network. Now, every access technology has its own unique set of control plane messages. And today, Magma supports LTE, 5G, and Wi-Fi. So we have, when data comes off the radio network, we split these two data streams to control and data plane, and we normalize all the control plane messages into something that we can reason about in a more generic way. We implement a variety of high-level services that let us think about how we manage the state necessary for running an access network. These are things like mobility, access control, subscriber management, session management, and crucially, our data plane configuration. The data plane configuration is responsible, or configuration service, is responsible for configuring our unified programmable data plane, which in our case is Open vSwitch. And by doing this, we can support a wide variety of network policies using the same underlying data plane, regardless of the access network technology they're connecting on. Now, these orange lines connecting services are internal Magma APIs that are all simple gRPC APIs that make it really easy to extend and reason about state within Magma. So you can imagine taking this to the extreme. All of those services I just described are simply software services running on top of an unmodified Linux kernel.
Thank you, Shadi, for sharing the scale-out network of Magma. The scale-out is just one part of the Magma story, which is built around the notion of the software-centric telco. The software-centric telco takes all of the services that have traditionally been delivered by specialized hardware from major network equipment providers and delivers that same platform as software to run only on general purpose data center hardware and systems. Great examples of this exist with Jio in India and Rakuten Mobile in Japan. Jio started with nothing and in 3 years built a network that rose to be the largest operator in India by subscriber base. Rakuten, using the same methods that Jio did and modeling their network approach, was able to build out a nationwide LTE network in less than 1 year from the start of their deployment, and did so at a cost structure that was significantly lower than the other operators in Japan, and allowed them to bring creative sales models to significantly grow the base. Magma exists to take this open source software and enable that for the 5G networks and bring LTE and 5G services to markets that have not been able to be served economically in the past. We intend to dramatically reduce the network total cost of ownership. Along with the story of scale out approaches, we'd like to do this through the Linux Foundation in a completely open source model. And we've constructed the Magma Core Foundation to do that in cooperation with the Open Air Interface Software Alliance, who's developing open approaches to the radio platform itself, and the Open Infrastructure Foundation, who has a long history of developing distributed systems on OpenStack and related scale-out technologies. We also have a significant body and growing body of partners in the foundation, led by ARM, Qualcomm, Deutsche Telekom, FreedomPhi, and a list that's longer than the list you see on this chart here. As part of this talk today, we're here to invite partners to come join us in this journey. We'd like to introduce the Magma Core Foundation, and you can visit us at magmacore.org and learn more about how to join the foundation itself. Our code is 100% open source and licensed permissively using the BSD 3 clause license, and it's available on github.com/magma. We also have a very dynamic Slack with over 1,000 users that have joined us on the Slack to talk about the ongoing development of Magma. And we do all of our operation in a completely open and public model as managed by the Linux Foundation. And you can find our regularly occurring public meetings at the link shown here on this chart. There's much more to learn about Magma, and we could only give you a brief taste of it today, but we'd love to have you join us on our journey. Thanks very much. There's a live Q&A session starting now to continue this conversation with Shadi and myself. To take part, join us on Zoom by clicking the yellow button just below the video player on this session's page.